Hello. Hello.
Hello, hello, am I audible? Hello, this is mic check for me. Hello, good evening. I asked the heads. Apparently, I'm audible. Hope everyone's having a fine evening. We're going to be doing a good session today. I don't know, I had a lot of fun drafting the session. We'll wait for a few more people to join in. Hello, hello everyone. Uh, is my voice better now? Like, I'll try speaking louder for the remaining part of the. I can't help it, bro. 1 second. Uh, oh, okay, 1 second.
Okay, now how's my voice? Is it better? Is my voice better? Hello. Oh, I changed my mic. Is my voice better than before or is it still the same? Oh, okay, sorry. Hey, Neelkant, hi man. Hello everyone. Good evening. Give me a second. I'll disconnect this. Bluetooth. We'll start. Just give me 1 minute. I need to disconnect one of my headphones. Hold on a second. I need to see his YouTube feedback. Okay. Are we ready? Oh, wait. I need to find out. Am I ready? Restart. Okay. Good evening, guys. I'm Roy Saldana. I'm from Mangalore. I'm a student of IBME, Instrumentation and Biomedical Engineering, a batch of 25. Along with this, I'm also an iBot coordinator. I saw a few of my friends in the chat here. Hello, everyone. All those whom I don't know, all those of you who are coming to IITM next year. I had a lot of fun drafting these slides. I hope you also have a lot of fun learning from this. This is a very basic module. I assumed zero prerequisites while drafting this. So everything that I'm going to be showing, everything that is going to be done here today is going to be fun and on a beginner level. So all I'm assuming is 1 plus 1 is equal to 2. So let's start. I hope 1 second. Let me just check my own live stream. So let's start. I hope 1 second. Let me just check. Sorry, that was my own voice. Alright. So good evening, guys. We're going to be doing Mechatronics today, intro to Mechatronics. There'll be a follow-up session on this, CAD designing, taken up by Ayandeep, but that's later on, I think on the next week onwards. So let's start. One meme that I inserted, so I don't know. I had one Tamil friend who used to call mechanical as mechanical. Luckily we don't study together, but yeah, a little bit cracked he was. I hope none of you are mechanical people. Okay, let's begin. So in today's course we are going to be learning a small introductory, a few slides I'll spend on what is mechatronics, very basic, just mechanical plus electronics when you combine the two of them. Then we have the sense, think, act loop, the loop that all systems, maybe even human systems, living systems, non-living systems, they use for decision making to actually make a physical movement. Anything that involves some level of logic or decision making always passes through a sense, think, act loop. Then we have the major section of this, which is going to be building blocks of mechatronics. Under that, I'm going to be showing you the various components, hardware that we might come across while building stuff, or software that we might need, or even the logic and the codes and basic workflow that we might be encountering while doing anything relating to mechatronics. And the final part of our session is going to be dedicated to dynamic systems modeling. It's a very fun name, DSM. And in this we are going to be basically running simulations inside our computer, trying to simulate something physical inside our computer. I think that will be the most interesting part of it, so please hang on till the last and let's begin. Summer School of 2026. What is mechatronics? So here, I don't know if all of you guys recognize everything that's on screen here. That's a Roomba machine that's used to clean houses. This is a drone that lost one of its motors, I guess. This is a self-parking car, and this is a thermostat. So these are introductory level examples for mechatronic systems, or systems that involve some form of robotics, some form of decision making that we might have encountered in our day-to-day lives, except for thermostats. I don't think any of us in India use thermostats. We'll get into everything, like basic decision making that goes on behind these robots and stuff. Sorry, am I lagging? If I'm lagging, I'll just restart the explanation of. No, that wouldn't be too time convenient. Um, okay, if I was lagging, my own life systems that involve some form of robotics, some form of decision. Is it still lagging, guys? That we might have encountered in our day-to-day life. Hello? Am I lagging or is my video being shown visibly? Hello? I think my net is a bit bad. Give me a second, guys. I'll just. Hello? 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 Am I lagging or is my video being shown visibly? Hello? Until I get confirmation from the heads, I won't resume. Hello? I think my net. I think my net is a bit bad. Hello? Hello, am I online? Give me a second, please. I'll just. Hello, am I online? Hello? Hello? Am I having my video? Okay, guys, I am not so sure how much you have missed, but from that previous slide it's fine if you have missed. It's just I've put an introductory slide. There's nothing much that I've actually taught. Everything, all the interesting stuff is yet to happen. So I'm going to resume. I'm really sorry for all the interruptions. I'll resume with my video off for another 10 minutes. So let's continue. So mechatronics, the discipline by itself, consists of three verticals that are integrated into each other: mechanical, electrical, and software. You cannot use a purely mechanical device. So suppose if I had to give you an example of a purely mechanical device, it would be a printing press, the ones which were used in the 19th century, like the wooden printing press that was used to manufacture papers by hand. That has, the hardware is built for exactly one function, to print a paper or maybe to print on sheets, and that is the only function it can serve. It can only print specific block letters on one kind of paper. These are examples for purely mechanical. And then purely electrical are LEDs. Can there be other purely electrical devices? Maybe motors? Yes. So these also they run as a virtue of their mechanical, the way they are mechanically built. So a motor is mechanically built by putting together solenoids and electromagnets and making them run by turning on their current. So but under mechatronics, we try to combine these two disciplines, trying to combine mechanical and electrical disciplines to create a machine or a system that can be repurposed, can be reused, by not changing the hardware or by not changing the dynamics of the system itself. Just by changing code or just by programming our code differently, we can achieve a variety of functions that were previously not available to us just by the use of sole mechanics. So for an example here, a modern day printer, the printers which we see in shops or if we have in our homes, it can print A4 flyers, it can print posters on gloss paper, oil paper, it can print barcodes, it can print greeting codes, all with the same gear. It doesn't have to, you do not have to change any physical functioning of it, you only have to give different instructions. So this is one way where mechatronics is very helpful. You can repurpose your gear without changing anything except the code or the instructions. Alright, sorry, 1 second. Yes, so we have our next subtopic that we're going to be taking up, called the sense, think, act loop. So as I already mentioned, sense, think, act loop is the basic flowchart through which any autonomous system that is making sense of its environment or moving around in this world, it always falls back to this particular act. So even human beings, for that matter, is, suppose if you're walking, or if while you are walking on level terrain, you will first open your eyes and ears, you'll use your sensory organs to make sense of the environment around you, use that information in your brain to decide what to do. Suppose if you're standing on level ground, your brain will tell you probably you should not go jumping on this level ground, or you should not go crawling or rolling in the dirt. You should just lift your legs up one at a time and walk. So that part is thinking, and you actually act. So whatever communication is given by your brain, it is communicated to your muscles, and you are able to perform some locomotion. And again this loop continues. After you have moved, because of your actions, your environment is again changed, which means your brain will again sense it, think about it, and make you act. So this loop is used in all mechatronic systems. Anything that you want to not just automate, anything that you want to function in a safe and stable manner, you will always try to get it back to the sense, think, act loop. So here I just put an example of, suppose if you have 11 robots playing the Robo World Cup for football, World Cup for robots. Again, you will have a boss robot, the brains of the robot, who will get information from all the other robots on the field. So other robots on the field will process their data by giving some images, maybe information from other sensors like proximity to the ball, state estimation, where each of the players are. Are they offside? Are they inside the field? Are they on the goal post? Are they in some random place in the stadium? We use all that information and we use our brain, our boss agent, to think about it, to coordinate all 11 players on the field it can select actions for each of them. Suppose take the ball or keep the ball with yourself. It also does motion planning. Motion planning is basically the same thing as deciding actions for your bots, and then the actions are actually carried out by the bots themselves. This the signal is relayed to them, and they perform. Maybe some of them run backwards, some of them do a backflip. This is just the sense think act loop, and immediately at every time frame, maybe every 5 milliseconds, the robot keeps on running through this loop, or the system runs through this loop, and based on the changing dynamics updates its decisions. So I think I've already explained what this is. It's the mechanical equivalent of human decision making. The bots gain awareness through sensing. They think with their chip, and the action that they actually perform is in response to decision taken by a chip based on its input sensory data. Alright. So I just now mentioned a sense slash think slash act loop. I hope I'm still audible. Let me just take off 30 seconds and check. Okay. Yeah. So what is an example of a feedback response loop that completely surpasses the think part of the loop? So as you can see here, I have used sense, think, act. Now remove, like, the sensory part and actuatory part are in some sense actually present, but the think part is removed. Like, you do not have a physical chip that is actually thinking. So what kind of controls in some kind of system would you say you have come across in real life that actually does this? Like, it controls the level of something. Suppose how do I give an example? You know what, should I give the answer? No, I'll not give the answer. So the think part of the loop is not done by a chip or anything. Instead, it is a property of a material that you're using. So maybe you're using some kind of special joints, or maybe you're using some kind of special metallurgical material, like some metal or maybe some component or some special plastic, that because of its inherent properties, it itself acts as a maybe a switch, or maybe it is acting as a valve, something to control rates of flow, or maybe to control decision. No, not decision making. It's just a switch. Yes. So guys, can you think of anything which would like, you have the think part of the loop not done by a chip, but maybe by some kind of inanimate object that does not need electricity, it does not need anything, it just functions like it is? Diodes are diodes. Yeah, it is a property of the material itself that it reduces it creates a voltage barrier. Yeah, diodes are a very good example. It controls some kind of flow. It controls the flow of voltage. Like, assuming you can call it, it's a very loose term, but yes, you can say diodes control flow. Presence sensing doors and malls, I'm not so sure about that. Geysers are very close to what I'm going for. Actually, I think I can give it to you for geysers. So reflex action in humans, we are still thinking about it. Fuse is a damn good example. I'm sorry I did not pick up on that. Bimetallic strip, exactly. Who mentioned bimetallic strip? Thuriak 6383. I had written bimetallic strip, but I've got amazing answers here. Geysers and diodes. Smoke detector extinguishing, I'm not so sure how it works. So basically what I was thinking about is temperature regulation in an iron box. Because of you know what, I think I can put on my video again. If it again starts buffering, then I'll turn it off. There's a big risk, but let it be. So what I was thinking about is a bimetallic strip in an iron box. Essentially, a bimetallic strip is two layers of metals that are joined together longitudinally, but one has a different rate of expansion than the other, so it heats up faster than the other. So when you're supplying a constant amount of heat through your electrical power circuit, one material will elongate more and it will start to bend the entire piece of metal. This acts as a kind of a switch. The entire piece will curve outwards and it will break the closed circuit that was maybe running over this end with your components as well as a wire running through it. So your bimetallic strip, essentially because of its inherent properties of uneven expansion, it itself functions as a switch and breaks connection. Another example that I thought about, I did not write in this slide, is controlling the water level in a flush tank. So essentially, after you flush in the washrooms, the water level by itself is maintained, right? It's maintained because of a floating ball, and to that ball, a small joint is attached, and the joint itself is pivoted at some kind of the input valve wherever water is coming in. So like eventually, as if enough water fills, the floating ball comes up, and the joint is horizontal, which allows the water to it blocks the flow of incoming water. So that's also a very good example for decision making loop that does not involve any sentient components. All are passive components. Yes, so I already explained this. So we'll move on to our next topic, the biggest topic of our slide, this was of our presentation, building blocks of mechatronics. But before this, I'll just give 3 minutes for everyone to scan this, open the G form, and mark your attendance. There will be another QR code like this towards the end of the session as well. So please mark your attendance. I'll wait for 2 minutes in that. Guys, another half minute. Okay, I think 1 second. Yeah. I hope I'm still visible. Okay, guys, I'm sorry. थोड़ा extend हो गया. It's fine. So let's move on. If anyone was not able to, then take a screenshot, or I'm sure, will it be sent? I do not think the heads can send this because this is a one-time attendance. It's fine, guys. Chill. Not that big of a deal. So let's go on. We'll start with the first part, building blocks of mechatronics. So here there are actually two components, but I should have put them on separate slides. For now, just focus on whatever I'm explaining. Sensors versus actuators. Just remember the loop that we just now talked about. Sense, think, act. Sensors address the step 1 of the loop. So sensing. I'm sure all of you have heard of sensors at some or the other point. Maybe you've worked with them at some point in your life, or maybe you've seen your friends working with it. So sensors are just electronic components that help the microcontroller or help your computer to make sense of its environment, to make sense of target variables. Suppose you want to measure humidity, you will use a humidity sensor. You want to measure light intensity, you might use a photoresistor, some kind of thing like that. Sensors are very simple. The name is self-explanatory. Do not focus on the sensors part now. Actuators are a new term, but basically they are just the output devices of your system. So I will not say computer or I will not say machine. I will rather refer to it as system. If I make a mistake in the somewhere in the middle, please feel free to point it out. But actuators are the means to measure output from our system. So if you talk in a robotics perspective, actuators are usually mechanical joints. So like you have a 3 degree of freedom arm or a 6 degree of freedom arm. You see it actually move in real life. Those are the best examples for actuators. Or actuators also, maybe you can extend the definition to LEDs or speakers. Anything that gives an output is an actuator. That's it. Actuators help the system to act, sensors help the system to sense. The thinking part, will come to it later. So these two devices are not opposites of each other, rather they complement each other in the system. So actuators that perform physical motion, the most common ones in robotics, usually use some or the other form of motors in it, normal DC motors or servo motors. There's not much to explain other than how a motor runs. But on the other hand, sensors are a little bit more interesting, how they actually measure voltages or how they measure individual components like pressure or maybe humidity from the environment and actually translate it to something that a computer can read in binary. We will come to this topic under ADCs, analog to digital converters. So I just have one small slide of sensors and I just put one big image of actuators. So at some of the other point over the last year, I have worked with a few of these sensors, not all of them. I do not think I can name all of them. If you guys know any of them, just please feel free to mention in the chat. I'll just wait for 30 seconds if you guys recognize any of them. I think over here there's a photoresistor module. This is a gas sensor module. Ultrasonic transducer. Oh, I think that's it. I'm out. Arduino. These are electronic modules. Like you can plug them into an Arduino, but I do not think exactly they are. An Arduino has a microcontroller chip that these fellows don't have. Ultrasonic sensor is right. UV sensor isn't. Those are IR sensors, infrared sensors. They use light that we cannot see to detect distance. Okay then guys, I think most of you know what's to some other level 1 or 2 sensors you can recognize. Okay, this is also a very simple laid back activity before we actually dive in. So if any of you want to give it a shot, just give it a shot in the chat. I'll wait for another minute. One is an actuator, that's right. Sensor, actuator, sensor, actuator, sixth. Sensor 2 and 5. 2 and 5 are sensors. That is right. Yes, that's right. I think everyone who has put answers till now are correct, except for anyone who has mentioned that 8 is a sensor or actuator. That's actually a trick question. A thermostat is neither a sensor nor an actuator. Basically, a thermostat just regulates external temperature and tries to get it to a target temperature that you yourself set. So this actually comes under the category of mechatronic system by itself. It cannot be classified as either a sensor or an actuator. It uses both as well as a chip inside. Okay, I think that's enough. Now let's start diving deep in. Our next topic which we're going to cover is microcontrollers and embedded systems. So microcontrollers, you've heard this word in several places. I think even you've seen Arduinos, you've heard a lot about Arduinos. So Arduinos come under the category of microcontrollers. So basically, in the sense think act loop, the second part of the job is on a robotics level. The second part of the job, the thinking job, is actually controlled by microcontrollers. So you can use your microcontroller units to run low level loops, like if you just want to perform brute force repetitive actions over and over again. So you want to host, suppose you want to run a loop 1000 times in a second or 1000 times in a millisecond. That is also possible with a microcontroller. Or you want to have you want to control two different components at the same time, or control one component based on the response of other component, or you just want to do simple if else statements with using your sensors and actuators. A microcontroller is the perfect choice for you. So it is optimized, it is basically built for only efficiency, for using low power, and for being as quick as possible, but only with low level tasks, like as I mentioned. So to give an idea of distinction, a high level task would be you give a computer an image and it tries to remove the background from the image. A computer can do that, but for a microcontroller to go through models and segregate the subject from the background and actually isolate those things, a microcontroller will blow itself up. It cannot handle such high level tasks. So examples for microcontroller units are Arduino Uno and ESP32. Arduino Uno is this one. I think majority of you guys might have seen this, maybe even in real life, in school projects or something you might have used somewhere. This one, on the other hand, ESP32, is slightly more costlier than an Arduino Uno, but it's got wireless capabilities. It's got Wi-Fi, Bluetooth connection, so it can be used to control things that you wouldn't want to use wires for. So the second part is embedded systems, which I have not yet touched upon. Embedded system is actually a very umbrella-ish term. It doesn't refer to anything specific. So an embedded system is just a combination of your hardware and software to make one machine that senses, thinks and acts. So there's nothing special about an embedded system per se. Just any mechatronic system comes under embedded systems. All you need to do is just have those three parts of sense, think, act loop integrated into your embedded system. So washing machines, airbags, they all function as forms of embedded systems. I don't want to spend too much time on embedded systems. There's nothing much there. Very important clarification, guys. If any of your friends, when you send them the slides and they ask you what's MCU, please do not confuse it for the Marvel Cinematic Universe. Disclaimer has to be noted without fail. Thank you. Okay. Microcontrollers and embedded systems. We are still going on with the same topic, but now I want to talk more about sensors. So here is the interesting part. A few slides ago I mentioned that I'll be taking up ADCs, analog to digital converters. So first let us understand what these words are. Analog and digital. Analog is basically anything that is recorded continuously. So suppose, whereas analog is anything that is recorded continuously. Digital is anything that is recorded or observed in time intervals. Like you try to build up a function, suppose build up a function by taking intervals at every instant. Let me try to give an analogy for those of you who have studied differentiation and integration. When you write the initial formula, the definition for differentiation, you write f dash of x is equal to f of x plus h minus f of x divided by h. Like you will approximate f dash of x to be that. So that is kind of the idea of digital. You're trying to measure change, or you're trying to observe anything that happens between a time interval of delta h. But as that limit h, delta h, tends to 0, you start to say that the derivative f dash of x is more and more accurate, correct? In the limit that h tends to 0. So in the limit that h tends to 0, when you're observing your variable at every single instant, that is what you call an analog signal. An analog signal is something like the stretches that the time axis may be the real numbers, and your observed quantity is measured for each and every real number, whereas your digital signal is something that is measured maybe into only terms of integers. Like your time axis may be only in integers, like your first second, third second, and only in intervals of 1 second you are observing some quantity. So sensors produce analog signals, but MCUs can only understand binary code. They can only understand 1001. So how do we convert our analog signals into binary code? 1 second. Okay, yeah. How do we convert them? We convert them using ADCs, analog to digital converters. So here I'm going to do a little bit of binary hand waving. I hope it is followable by all. I will not do this slide first. I will first show how does binary work. Okay, so suppose for those of you who do not know how binary works, or if you just want me to refresh your memory, if this is a binary number 10011, we, based on each unit digit, we try to assign a weightage. So we'll assign a weightage to this digit based on its position in the number. So we'll assign a position of 2 power 0, here 2 power 1, a weightage of 2 power 2, so on and so forth till 2 power 4. We have 5 digits here, so we will be using weightages ranging from 2 power 0 to 2 power 4, n minus 1, where n is equal to 5. So after writing this, we just multiply each digit into each weightage, add them up to get the number in base 10. So when I'm converting this binary number into base 10, I'm going to be doing something like this: 1 into 2 power 4 plus 0 into 2 power 3 plus so on so forth, which is nothing but going to be 16 plus 2 plus 1. So 10011 in binary in base 10 system is 19. So this is how binary works. Let me get back to what I wanted to show. So as long as you know how binary works, now I'm going to show you the way how ADCs convert an analog signal into a digital signal. So suppose if you have a given range of voltage, like I told you previously that you could only do between 0 volts to 15 volts. You could measure a voltage that could be either 0, 1, 2, 3, 4, 5 or till 15 from an analog voltage. How are you going to do this? I will tell you. We are going to use a 4-bit encoder, and we are going to find this voltage in a maximum of 4 steps. So how does it do this? Yeah, if it's too much of jargon, then I'm sorry. I will explain this and then get back to my original slide again. Okay, so suppose we have a test voltage 11 volts. I'm giving you an example because I think with an example it will be understood best. The job of my ADC is to output 11 in binary for my MCU, which is 1011. So input is going to be 11, output should be 1011. So it is going to test the most significant bit 1. So if you saw here, out of all these, the most significant bit is the one with the highest weightage, 2 power 4 here. It's always the one which appears on the left. So I'm going to start testing from the most significant bit. So for this first bit, I can either guess 1 or 0. So I'll start with testing 1. Okay. So guys, I want you to focus on this flow chart. I'll try to go slow with this, but I hope everyone understands what's going on here. So my first most significant digit, I have put it as 1. The rest of them I've all put them as 0. So 1000 in binary is going to be 8 volts. So I'm going to test my test voltage against this 8 volts. Is test voltage greater than 8 volts? We know that test voltage is 11 volts. So the computer will most likely give the answer yes. 11 volts is greater than 8 volts. So the first bit has to be 1. So the computer in this if-else loop, it has decided that the most significant bit is 1. First bit is over. Now we have to compute our second bit. So the value of our signal in binary is going to be 1xxx. Is this clear till now? Okay, so now our computer is going to determine the second bit value. How is it going to do this? It's going to test second bit value. As I said, since we do not know what the second bit is, we'll try to guess it is 1. If it gives a good result, we'll keep 1. If it is not, then we'll keep 0. So here we have put 1 here. So 1100 in binary is going to be 12 volts. So is our test voltage 11 volts greater than 12 volts? Anyone replying? Okay, I don't think so. So our test voltage is less than 12 volts. So our second bit is not going to be 1. The guess for the second bit was wrong. The second bit is going to be 0 instead. So right now we have confirmed that it's going to be 10xx. So we'll continue with this flowchart from here. We are going to find the third bit and the fourth bit for this particular value. So second bit is not 1. The value is 10xx. Third bit, it will guess it again as 1 in binary. The fourth bit we do not know, so we have just kept it as 0 as a placeholder. 1010 in binary, it's 10 volts. So our computer only knows how to match and mix voltages. It's going to check, is test voltage greater than, equal to, or lesser than. 11 volts is greater than 10 volts. So the computer is going to say yes. So the third bit again is going to be stored as 1. So finally the value of our binary number is going to be 101x. We still do not know the fourth bit. It could either be 1 or 0. So for every unknown bit, again we are going to put the value 1 and check. So once we check if it's 1011, in binary 1011 is nothing but 11 volts. So test voltage, it matches to 11 volts, and thus our ADC, in the span of 4 steps, it has given an output to the MCU saying that the analog signal measured by our sensor is 11 volts. So you see, as you go back along this flow chart, even though it might have been a bit hard to understand at first, basically it read a voltage between 0 to 15 volts in exactly 4 steps. Like at maximum, an ADC needs only 4 steps to read any voltage, provided it's an integer voltage. I cannot guarantee the same thing for 2.5 volts. You know what, for an assignment we can keep that. If it is 2.5 volts, what will be the binary output? Because our test voltage is going to be 2.5 volts, and at every step along the way, all we are going to be doing is we are comparing test voltage versus some binary voltage that we are given. All you have to do is keep on checking if 2.5 is greater than 4, 2.5 is less than 9, something like that. I'll give a set of decimal voltages in my assignment to test what would be the output by a 4-bit encoder or 12-bit encoder. But essentially, the encoder we use, the ADC, analog to digital converter we used here, was 4-bit. 4-bit means it can check any value between 0 and 15, integer values only. Here also, here it was 5-bit, the example which I gave. So it could check any value between 0 and 31. 32 is 2 to the power 5, so it can check from 0 to 31. Analog to digital converters, okay. I think that is it. 4-bit encoder was able to solve the problem in 4 steps rather than looping through the entire set of integers 0 to 15 exactly once and doing 16 steps. So it has, instead of 16 steps, it has found the voltage in 4 steps. So it's pretty efficient by using binary. Okay, for our next topic, we are going to be doing control theory. Do you text like this? If you text like this, I'm proud of you for learning control theory. I'm sure I've seen a lot of my friends using these in their texts. So lol k, lead or lag. I'm sure that's what all of us text. Okay, let's begin with control theory. Okay, so now we have all our hardware in place. I mentioned sensors in the beginning, actuators, and we have our thinking done by our chip. But these are all hardware components. How do we put the logic into these hardware components to make them self-sufficient, autonomous, and they are able to make a decision? That is controlled by control theory. Sorry for saying control twice. Control theory is the logic that dictates how all our hardware components in our system should interact with each other and work for a particular goal. So control theory, at its basic level, you could say it's maybe an if-else statement, or you can say while. It's just a simple while loop. While action is not accomplished, please do action. So something like maybe a bell. You can tell the bell to keep on ringing for 5 minutes. But let's try to classify all these processes under 2 terms: open loop and closed loop. So am I going too fast? Okay, I think I'm visible, right? Yes. Sorry. So under control theory, we have 2 loops: open loop and closed loop. Do not get too much hung up on the loop word. I'll explain to you before I go to the next slide. So in an open loop, our microcontroller gives an instruction to an actuator, or it tells do this output, hey, do this output for another 5 minutes, and then stop it, and I will not look at how you have done the output. So suppose if you suppose you were a kid and your dad asks you to fill water in the bucket before bathing, he'll tell you, bro, you turn on the tap for 5 minutes and leave it, and then I'll go and put it off. So when you do that, you're not seeing if the bucket was already filled. You're not standing there and seeing if the bucket had a hole where water is coming out. You're not standing there and seeing if the bucket is already overflowing. Your dad told you, put the tap on for 5 minutes and then come out. Done. So that is an open loop system where you do not monitor the output. You are told, do this, and then maybe stop doing that and end it. So here you're not monitoring your output, and this is very dangerous. You cannot no self-sufficient system would want to be open loop. It's like telling a blind person, you walk ahead for another 30 meters and keep on walking, and if you hit a dead end, it's your fault. I told you to walk for 30 meters, and in my scale 30 meters means you'll stop right in front of the in front of the dead end. So something like that. Open loops are harmful for any self-sufficient system, where we turn to closed loops. So this is what an open loop system is. The control action is independent of the output. The controller sends command and says, Bhagwan pe bharosa, this thing is going to run as it is, all right, I am chill max. So this is not the way a closed loop system works. A closed loop system constantly monitors the output to ensure that the input doesn't exceed bounds, or it tries to control the input based on the output. So it's always a continuing loop. So how do I give an example for this? In fridges, let's say, no, let's take the example of human bodies. Our own temperature, we are warm-blooded animals, so our body temperature is constantly maintained at 98.6 degree Fahrenheit. Correct me if I'm wrong, but I think that's our body temperature, regardless of where we are, whichever part of the world we are in, whichever human beings normal body temperature you check, it's always going to be 98.6 degree Fahrenheit. This is an example of a closed loop control system where it constantly monitors the environment. It constantly monitors maybe if you are in an Arctic region, or it monitors if you are in the equator or in some hot place, and it constantly makes sure that your body adapts to the external temperature such that your body temperature is the same. In a closed loop system, our sensors continuously measure output, and it compares it to the desired goal. So maybe when you're filling water, your desired goal is to fill the bucket till 3/4, and you will keep on looking at your bucket until the water has reached that level. This is called a closed control loop. You will always try to minimize the error. That is the entire aim of your existence. So if you try to look into the semantics, the loop word is more appropriate when you say closed loop. Open loop as such is not a loop, it is just open. But closed loop helps you to keep on monitoring, and you keep on going in a back and forth cycle. Of course, it's harder to program, but it's more safer for systems. So self-balancing, so just put in a self-balancing robot like this one. It uses closed control loops to monitor the position. You would use an open control loop in this situation if you had a robot with 4 wheels, where you are guaranteed that this robot cannot collapse by itself. But here this robot is highly unstable, so you keep on monitoring its positions, and if it's changing its angles every like maybe 50 times each second, and ensure that it is upright. So another we are continuing with control theory. So the most common control mode used in the industry is a PID controller, proportional, integral and derivative controller. Sorry about that cup. So a PID controller is a type of closed control loop system only. This one is exclusively making use of a PID controller. So P stands for proportional. The response of the system is proportional to current error. I is integral, and D is derivative. So here I just want to make one thing clear. The target variable, which we're always monitoring at every step, maybe 60 times every second, we are always looking at the error. We're looking at how far our system is compared to the desirable goal. So each term of this PID controller somehow or the other uses the mathematical knowledge of the error. So P is proportional. It gives a response of the system that is proportional to current error. If you don't understand that, I have a small simulation. I'll show you about that. Integral and derivative, for those of you who have already done calculus, or maybe if you're learning about it right now, it's okay, you can stay with me about this. It's not like you need knowledge of calculus for this. So integral part of the code, it keeps on integrating errors over time. So it keeps on adding past errors and keeps on making a sum total to let the system know how well it was performing in the past. So if it was a bad system, then maybe the errors are keeping on compounding, which forces the system to get better. D is derivative. It takes the slope of the current error to let the system know how to perform in the future. So at every instant you calculate the derivative of the error slope. Again, it's the error graph that you are plotting, and you're going to look at you're going to estimate, okay, maybe if I'm continuing on the same trajectory, in the future I'm going to reach this part. It may be favorable to me, so let me continue like this, or if it's not favorable, I should avoid it. So even if you didn't understand how the mathematics part of it works, just remember that the P part relates the next output of the system based on the current response, the current error. Integral part of the system bases the output of the future output of the system based on accumulated errors, like it's looking at the past. And D is for the future, it's trying to predict the future. So it's trying to predict the future error, and hence is a measure of the future error. So in this, using the PID controller, you have accounted for all three states of time in which your errors can possibly accumulate for your system. So here is an example of proportional control to build a bot that follows a target. So I've got a Python program for this. Just give me a second. Where's OBS? Give me a second, guys. My stream. Display capture. Okay, I think you can see my settings. Okay. Okay, so this is a proportional controller. I will play it first, and then I'll explain to you what is happening. Okay, so proportional control tracking. So I will explain what are the basic components on the screen here. Do not have to understand why this looks so bad. So we have a tracing node. I have a node, the green node. Wait, I think this is a bit distracting slightly. Okay, I'll just keep it like this for now. Yeah, so we have the green tracing node that is constantly going in a circle. Like I have set it to move in a circle at a constant speed. So the green circle that you see here that's getting traced out is actually its locus. The red part is a tracking node. So the tracking node is my system. I want my red node to follow the green node to the best of its abilities. Like in the ideal world, I want the red node to overlap on top of the green node. But sadly, as you can see in my example here, my red node is moving in a very small circle as compared to the radius of the big circle. It's not performing its duties efficiently. So how is this actually working? So let me take a screenshot. Give it a second, guys. My video is lagging, huh? I'll turn off my video for now. Hello. Hello, sorry about that. I have turned off my. What have I turned off actually? I've just turned off my video. Oh, I'll resume. Is it all right now? Yeah, my video is off. It's still lagging. Is my audio fine? Hello, is my audio audible? Okay, it's not yet updated. It's sorry about that. Sure. Sorry about that. Okay, the audio is fine apparently. Is my screen getting shared? One second. Okay, continuing, stopping this. Okay, I'll try to abandon that. I've got already screenshots of how it's functioning. I'll just switch back to my current presenter view. My stream, properties, display capture, application capture, application, window capture, camera. Okay, the audio is fine apparently. Is my screen getting shared? Window capture. Okay, continuing, stopping this. Okay, I'll try to abandon that. I've got already screenshots of how it's functioning. I'll just switch back to. Okay, guys, I won't be. Sorry, I think this might echo. Okay, guys, I won't be using my camera for the duration of the session anymore. Sorry about that. So let's continue. So here I have got my tracking node trying to follow my tracing node. How does this work? This works by taking the red node and the green node. It tries to compute the difference between them, like the vector difference. So it draws a position vector between it. As you can see, the small gray line. It takes the unit vector. I think a unit vector is basically just a vector with direction divided by its magnitude. So you will get the direction of the vector and you will multiply that by a proportionality constant. Proportionality constant is going to be Kp here. So let me show what I mean. So see, Kp here I will set a proportionality constant 2, which multiplies itself into the error, the distance error that is there between the green node and the red node. Here the error, suppose if the magnitude of the error was 0.1, then the distance traveled in this direction will be 0.2. So it will construct a new vector for this red dot that will go 0.2 units in the distance of the position vector. How did you get the position vector? You know the direction from unit vector, and the magnitude you calculated it as Kp into error, 2 into 0.1. So distance traveled will be 0.2. That is how at every moment you are trying to minimize error by going in the direction of where the error is. It is not going tangential to the actual figure. Like if I had to change this circular figure to something else, maybe if I were to change it to a figure 8, then we'll have a much more interesting path. I should have done that, but yeah, I've not done a simulation. I'll give you the code to do the simulation by yourselves later on. Sorry for this streaming cup. Okay, we are no longer doing the circle now. Now we have gone on to the last part. We are currently doing power and interfacing. I hope everything is fine. I'll just check with the heads. Okay, yeah. Sorry about that. Power and interfacing. So not all your components can be directly powered by your MCU. Your MCU is supposed to be lightweight, low level, just made for doing simple first order computational loops, and it's not expected to give out a massive amount of power, like enough to charge your phone. Like your own your laptops and stuff can charge your own phones, right? But that's not possible by your MCU. Your MCU operates at very low voltages, 3.3 volts or 5 volts, and extremely low current, milliamps. So you wouldn't even get shocked if your microcontroller tried to haunt you. So the moment you try to power a heavy motor from your microcontroller pin, you will burn out your chip. So what is the solution to this? I will just try to give the example that you face every day in real life. When you try to, when your light is on and working, you are not physically powering your light. You are not sitting there on a cycle trying to cycle uphill, generate some rotational energy, kinetic energy, and power your tube lights through heat. No, you do not use your energy for that. You have already plugged an energy source. Your energy source comes from some energy supplier. Maybe in your place it might be Bescom, Tescom, some random Escom. But where you put your energy is in moving your finger to touch the switch and put it and turn it on. So this is one example of where you are using your minimal energy to turn on an appliance that requires far greater than energy than you can ever supply. So this is something that is handled by motor drivers and power electronics. So we use power electronics to manage high energy flow. All we ask the microcontroller to do is to turn on and off the switch that connects the huge circuit. The circuit will have a heavy duty power supply and a heavy duty load. All you want to do is close and open the circuit based upon your microcontroller's instructions. So you can use these following electronics: MOSFETs, transistors. They're very tiny. H bridges. It's an IC chip. They just give a signal to open or close a gate, allowing your power supply to power your motors or whatever components you have. Also, you can use the analog signals that you get from your sensors are probably going to be messy or noisy. So you will use this an op amp probably to as an interface before you send the signal to your MCU to amplify or to clean your signal or to remove spikes from, I don't know, noisy observations. That's where you can use interfacing electronics. Now we move on to the last part, dynamic systems modeling. In my opinion, this is going to be the most interesting part of today's session. I hope everyone has Google Colab working. I sent a link up yesterday. I'm going to paste links in that, and I'm going to paste code in that, and you can copy that into your own notebook and use it. So, one second. If you have not got the link of that, if you have not got that, I'll ask the heads to send the link. 1 second, or I'll send you. Fine, go ahead. 1 second, guys. Just give me a second. I'll send you all the link for where I'll be uploading code. Check your WhatsApp. Is it lagging again? @Ciscosphere. I don't think the link has come yet. It's not yet sent from my WhatsApp. Guys, if it's not shown, heads, if you are there in the meeting, Okay, it's sent on WhatsApp. Heads, if you're in the meeting, could you please copy and paste the collab link from what I was sent yesterday? I mean, in the morning on the group. Just send it on the YouTube chat as well. That will be our collab link where I'll be uploading code now. So, okay, guys, dynamic systems modeling. So, what is dynamic systems modeling? DSM. So, DSM is a fancy term to refer to modeling your physical world or making a simulation of it inside your computer. So, if you were trying to release a prototype for a new car, you'd probably, instead of building the car and driving it out like a normal human being, you would be a Fundu researcher and model your entire car inside your computer and try to see where your systems are really heating up. Suppose if you want to measure the maximum temperature your engines can go to, you'll model your entire car inside your inside your I don't know, MathWorks. I'm not getting the name. MathWorks or SimScape or Simulink, and you will test it under different conditions such as driving up a slope or overtaking or drifting, something or the other. So we are going to be doing a demo of using a concept called FDM, finite difference method, to model colliding blocks. That is our first activity, and the second activity is going to be blocks attached with a spring. So I'm pretty sure you'll find all of this interesting. The math is not very hard to follow. If it's hard to follow, just I will say a few events. Trust me, bro. I think you can trust me without needing to know what is going on in the background. So let's begin. I'm stopping my OBS sharing and I'm going to open it in a different window. Filters, properties, method, display capture. Right now it works. Firefox page. Where is my code? Give me a second. Okay. So let's start with this is. I hope everyone has set up Collab. I mean, there's nothing much to set up in it. It's all online only. So there was initially the first cell in which you should, ideally if you ran it properly, you'll see a red block moving at the bottom of your screen. So I'm going to copy different code now. Okay, so this is our code that we are going to be using to model collision between two blocks. So I have given most of the code here already, so there are a lot of import statements as you can see here. I'll explain what are classes and objects in like just 2 minutes. I'll just show you what and all is not. Okay, everything is given here in fact. So before we begin, some of you might already have used Python before and you know what classes and objects are, but even if you have not, just bear with me. Even if you do not know Python, all the syntax and code that I'm going to be showing you here today is very understandable, I would say. So yeah, give it your best shot. If you still can't understand, later on after the session I can help in explaining the code, but give it your best shot to try to understand what I'm saying now. This is for everyone who is not familiar with Python or object oriented programming. So a class, I will use only examples from what program we are writing. The class block, here I'm going to build blocks inside my own computer. So inside my own computer I'm going to build a world for my blocks. My blocks are going to have the following properties. 1, they're going to have a position. I'm going to assign them a coordinate system. 2, I am going to have them with some velocity. 3, I'm going to give them some mass. 4, I'm going to give them some size to make them look big or small. And 5, I'm going to give them walls. All of these blocks are going to have walls. So every block, when I create a new block, I am like a creator in this world of my computer. So when I create a new block, every block I have to give position, I have to give velocity, I have to give mass, and I have to give size. But different blocks that I make might not be the same, might not share the same characteristics as each other. For example, one block might have mass 1 kg, other block might have mass 10 kg, another block might have 3 kg. These are separate objects of the same class. So the class is block, and out of block I'm making 3 separate different distinct blocks with the following properties. In my world, they obey my rules, and my rules are: you should have a coordinate system, you should have velocity, and you should have mass. So this is the initialization program for any object block that you are creating. Define update. So dt is the small time interval in which we are going to be running a simulation. Okay, sorry, I never explained what is finite difference method. So finite difference method is basically when you split your time interval. Suppose you want to model a system for 2 seconds, you split it into multiple time segments. You split it into, maybe every second you split it into 100 elements, and at the end of each time element you keep on rerunning the same laws of physics, the same equations governing the system, and try to update the future position of your system. I hope this is like you understand what I meant. Finite difference. So there's a finite time interval between two successive iterations of the loop. So suppose if I was running a loop at 60 fps, so there are 60 frames per second. So between two iterations of the loop, there is 1/60th of a second that is lost in transit. So during this 1/60th part of a second, how much has the system changed is what my each successive iteration of the loop is trying to measure. Let's go to our summer school notebook. Where is it? Firefox. Got it. So that is what dt is here. Dt is the small time interval. This is so now you know what finite difference method is. Dt is the core part of it. Now here we are going to define a function called wall collision self. Whenever you see the self just means it's referring to itself, like its own object. So I do not know how to explain this clearly. If you have an object b1, when you say let me write in comments, I'm not writing this is actually called b1 dot check wall collision. I can either write self here, or I can choose to completely omit self, because the Python itself will ask the program to check against class, does it have a function that says check wall collision, and it will check wall collision exclusively for b1. Important, it will check when I use a function like this, it will go to self and it will check wall collision only for b1, it will not check for b2. For b2 you have to write a separate function, or maybe since it's an object of the same class, you'll have to ask it to check wall collision by itself, like this. Okay, I hope like this much was intuitive. Even if it's not intuitive, just try to follow along to the best of your abilities. So let's continue with what and all I have already defined here. Update function just checks the notebook position, sorry, not notebook position, the block position from the previous one. So self.x, the x coordinate of the new x coordinate at every instant, it's going to be the old x coordinate plus v delta t. This part I'm sure all of you have come across in physics. Dx by dt is equal to v. So a small change in position dx is equal to v dt. Define handle block collision. This method we are going to write. I'm going to show the logic and I'm going to give you the code itself. So hold up, I hope it's shared to all of you. Let me save this. Define wall collision self. Define handle block collision. These are all methods. I will explain why I have made two separate functions, and here we have to define blocks b1 and b2 and actually animate them. This entire thing you do not have to give even 1 ounce of your brain into thinking what this is. These are all animation, based on animation. There's nothing technical to learn here except how to write syntax. So let's get to our presentation. Okay. So here we are doing a demo of using finite difference method to model colliding blocks. So this is our basic flow chart. This is how we are going to be, the basic flow chart that is going to be run at every time step of our program. So after delta t, 60 times a second, the compiler asks, is block colliding? Now block can collide with two things. It can either collide with the wall or it can collide with another block itself. So we'll follow this path. If the block is colliding with the wall, then what is the physical response? I'm sure all of you have studied this. So if a block collides with a wall you can consider it as an object of infinite mass. So so we are considering elastic collisions here. So the velocity of the block itself will get reversed. So if the block is colliding with wall, yes, then reverse the velocity of the block. If the block is colliding with the wall and you check this and it says no, then do nothing. Eat 5 star, do nothing. Now if the block is colliding with another block, in elastic collisions I think you might have encountered how to write v1 dash and v2 dash. If not, I have written down the equations for you anyway. So you can look at those equations to determine if it's colliding with the block, how should the new velocities be. If it is not colliding with the block, then again eat 5 star, do nothing. Just let the loop execute itself all over again. 1 second, I'm just going into presenter mode. Yeah, okay, let's go to the next one. So see here, this is an example. If a block is colliding with the wall, okay, these are conditions. 1 second, have I not okay, see, ignore this slide for now. Okay, note this slide. These are the velocity transfer equations for blocks 1 and 2. So you do not have to derive them over again. I've just written them as reference for myself when I'm writing the code. Okay, so how do we check if the block is actually colliding with the wall or with another block? So block is colliding with the wall. So this is a wall and this is our block. This dot in the center is the x coordinate of the block, and this is the origin of the system 0, 0. So what are the conditions? Wait, why have I displayed the answer? Do you guys know what are the conditions for the block to collide with the wall? Hello? Okay, it's fine. I'll just continue with it anyway. So for the block to collide with the wall, I have already mentioned that the x coordinate is the center. So it's if this is the width of the block size, so from this edge exactly measure size divided by 2 and you'll get to the center. So if it's doing a left collision with the wall, then self dot x is going to be less than self dot size divided by 2, which means that the x coordinate is somewhere lesser than the width of the block from center to edge. Same logic you can apply at the right end too. This is the same code that I have given. I think many of you are answering it correctly. Block colliding with another block. So this is another, see, do not generalize. Both the blocks might have the same size, they'll have different sizes. So for here the conditions will be the x1 minus x2. So the x coordinate of this minus this one, absolute magnitude of distance between them is going to be less than half the size of this plus half the size of this. I hope these conditions are clear. These are your if else statements. These are the velocity transfer equations. These are the velocity transfer equations, and now let us write them down in our notebook. So let's go to Firefox. Okay, so let's attack the first part. Define wall collision. How to write wall collision? So as you remember the conditions, if self dot x minus self dot size by 2 is less than or equal to 0, ignore whatever Google is auto recommending for me, then the first thing that we're going to do is we're going to set self dot x is going to be equal to self dot size divided by 2. We're going to set the x coordinate of the block exactly flush against the wall. Second part is we're going to reverse the velocity. Self dot velocity negative self dot velocity. Else if self dot x plus self dot size divided by 2 is greater than equal to self dot wall limit. So again I have set the so that the block will be exactly flush against the right wall, and self dot velocity is going to be negative of self dot velocity. What is wall limit defined as? Wall limit is defined as just the space in which our blocks are going to be colliding with each other, just the window. So this is our first part. We have filled in our first part of code. Second part is handle block collision. So how are we going to handle this block collision? We are going to use those velocity transfer equations. So let's go to velocity transfer equations. Give me a second. Okay, I think we're running a bit behind time. No, it's fine. Velocity transfer equation. Sorry, I'm just looking up for those equations. So let's set the conditions. If absolute value of b1 dot x minus b2 dot x is less than is less than b1 dot size divided by 2 plus b2 dot size divided by 2. Sorry guys, syntax thoda important. I think I made a colon error there. v1 new is going to be equal to, I'm just going to keep on updating the same equation. So you know what, I've already written it somewhere. I'll just copy paste from there again. I'll copy paste and then tell you what it is. Just give me a second. Is this the one? Yes, this is the one. Define handle block collisions. Yeah, so see here, when you're handling this function is your physics function that is called at every instant of your execution of the program. So it checks if the blocks are colliding with each other, and it sets the new velocity depending on the old velocity. So here, if this code bogs you down, don't worry, just copy paste this. This is the exact momentum transfer equations. Then after finding out the new velocity for v1 and new velocity for v2 after a collision between them, you set b1 dot v is equal to v1 new, v1 dot v is equal to v1 new, and v2 dot v is equal to v2 new. So you have updated the old velocities to match the new velocities, and after that again you're going to check if these new velocities are going to encounter with a wall collision for v1 and v2. So this loop is called 60 times a second to determine the physics of your update. So every time I already showed you the flow chart, what is going to be checked. Both block versus block collision is going to be checked, as well as block versus wall. These all are other parameters. Wall limit I've set 10 units, fps 60 fps, dt is going to be 1 by fps because 60 frames a second, so 1 frame is shown every 1 by 60 seconds. Time duration equal to 10, which means that there will totally be 600 frames. So for a time duration of 10 seconds I need to generate 600 frames. So now I'm going to define blocks b1 and b2. I've already written some blocks b1 and b2. Don't worry, everything I'll share it at the end of the presentation or latest by tonight. So here are our two objects, b1 and b2. Both are blocks but different masses, different sizes. See, this mass has 50 and this has a size of 2, and its x coordinate is much further to the right compared to b1. It's traveling with a negative velocity. So okay, if everything is good, then in your own Colab, just go to runtime, click on change runtime type, T4 GPU, select T4 GPU, save and reconnect. If it's not running inside the notebook I shared, copy the, sorry, something has happened. Okay, I have exceeded my usage of Colab. It's fine. I'm going to run this in Visual Studio Code. So I'm just going to show you how the output should look like. So once you run this code on your own Colab, or if you have a notebook installed, please check the video if it comes out something like this. So these are two blocks, one mass 50 and the other mass 1 kg, that are, okay, wait, that was not supposed to happen. Something glitched. 1 second. Wall limit, I'll just set the mass to 10. Just give it 6 seconds, it will load. I hope it's not too late for you guys. I'll wrap this up quickly. The spring part is actually kind of interesting. This will maximum finish in another 10 minutes. You guys are messaging in the comments. Sorry, I forgot to mention this. If you want to do it in 90 FPS, yes, you can definitely do it in 90 FPS. It works without GPU. Yes, it can work without GPU as well. Okay, I think my code is taking some time. It might have crashed or something. It's light. If anything starts glitching, just adjust the masses and make them not too much of a difference with each other. Yeah, see, it's back up here. This block is 10 kgs and this block is 1 kg. And yes, 10 seconds of iteration are over. Let's move on to the last part, modeling springs. If programming is giving an error after the session, I will share the code. You can use this for yourself. Okay, so finite difference method, a small extension to that. Now we are going to deal with differential equations. So this is an equation dealing with first derivative, x prime of t. I'm sure the people who are studying in 12th standard right now will recognize this. Even 11th standard you might have come across this first derivative function. This derivative looks at the forward rate of change. It looks at a time interval. If you're looking at time interval t, it looks at t plus dt and subtracts it from t. And this looks at backward change. At a time instant t, you're looking at the states x of t and x of t minus dt. And so I'm going to add both of these and I'm going to divide by 2. So when I add both of these, x of t and x of t gets cancelled. These numerators add to each other, and this 2 from this end I will take and put them in the denominator over here. Why did I show all this jugaad? Because I am going to make a magical step from here, and I'm going to show you how to write a second derivative by using an approximation. As you have kind of realized by now, every simulation that I'm doing using finite difference method, I am not doing a continuous simulation, I'm doing a discrete simulation. I am taking finite steps at every 1/60th of a second, so and so forth. So when I'm doing as such, I will have to make some approximations. So these are the approximations I've done for first order derivative, and since we're dealing with second order differential equations when we use a spring, here is the approximation for a second order derivative. So the derivation is a little bit complicated. It's not too undoable. 12 standards I'm sure will find it very easy, but I do not have time to show this. So please accept this at face value, and we will use this to solve our further equations. Sorry about that. Okay, so now let's work with springs. So first let me copy paste my spring code. PyCharm, Firefox. I'm sorry, where did I leave it? Left it in Firefox. So guys, this is the code for Spring. So here again I have used objects of the type block, same initialization features as before, except I have used a new variable called xprev. So for every x that I measure in memory, I'm going to keep one x of the previous state in backup memory. I will explain this why. So if you look at where is it? Yeah. If you look at this equation here, mx double dot is given. You know the equation for a spring, right? So this is the equation of a spring that we are going to be using for our 2 block wala system. But for a simple spring, just imagine I'm writing over here. Wait, can I write over here? Draw on page. Oh yeah, that's cool. So hold on. Yes. M x double dot is going to be equal to negative kx. This is something that you would come across in typical spring systems, spring-based systems. So when you replace this mx double dot, this x double dot, with the equation that I showed you on the previous slide. So remove my pen, go to previous slide. When you replace that x double dot with such a huge equation, you're going to be having, give me a second, yeah, you're going to be having, suppose if x at time t minus 1, x at a time interval t minus 1, x at time interval t, and here I'm going to put x at time interval t plus 1. So at any given point, what we can clearly see is that there are 3 states of x that are being observed. I need to know my unknown is at every instant I want to find out x t plus 1. How do I say this? At every instant I want to find the future x. Like I want to find, if I'm currently stuck at time interval t special or t star, I want to find the position of my block at the next interval, x at a time t star plus 1. How will I find that? By using my two already given coordinates. I'm given that the current position of x is x t star, and the previous one is x t star minus 1. So that's why it is important here in this equation. There is only one unknown. We want to know x at a future instance, for which we'll have to use x at the current instant and x at the previous instance. So that is why we have in this equation that I wrote in Firefox here. I merged these two. Wait, let me escape. Why is this not escaping? Yeah, okay. So that is why I have an x previous here. That is just to give a phantom value for x. So when I initialize my block at the start, I'll give it a coordinate, and I'll give it a velocity, and I'll give it a mass, and I'll give it a size. So suppose it was moving with a velocity of 5 meter per second. How do I tell the computer that it was moving at a velocity of 5 meter per second? I will create a ghost point. So x previous is a ghost point. X prev is a ghost point measured at time t minus 1. So it is measured at -1 second, -1 seconds or something like that, just to ensure that for continuity, like I can only calculate x1 if I know x0 and x minus 1. So this is just a conventional tactic. You do not have to give too much brain power into why this is put over here. Define spring force update. Okay, I have already given the entire code here. I will rewrite the code myself. Don't have to worry about that. This is a to-do list. To do. Rest of the part, this is how we should actually tackle our problem. I will show slides on how we are going to do it mathematically. This, on the other hand, all the things remain same as the last program. 60 FPS, 2 blocks, both with mass 1, but one has a velocity of 2 and the other has a velocity of 0. So, okay, how will we try to model our block? So, come. Mx, how do I erase this? Okay, I had to erase that, sorry. So mx double dot is equal to x1 is the x coordinate of block 1, x2 is the x coordinate of block 2, and L0 is the resting length. So I have replaced x1 double dot with the equation from over here. I hope this is you have followed the transition from this step to this step. Then we know x1 t minus dt and this quantity, so we'll try to figure this out. We'll rearrange for x of t plus dt to get this. So F is nothing but the spring force. Spring force is nothing but this, the first term that is mentioned over here. So x1 at t plus dt is going to be written like this. This is for x1. We can write the same code for x2 also, and that is exactly what we are going to write in my notebook right now. So where's Firefox? Sorry about it getting a bit late, guys. This is the last simulation. Okay, So let us copy paste the code, but I'll explain it line by line. So calculate the displacement vector. The distance between the two vectors is x2 minus x1. Current distance is going to be absolute value of displacement. So displacement has a sign, it can be positive or negative, but current distance is exactly is always positive because you're taking absolute value. So the second part of this is we are going to determine the direction of the force. So direction is going to be displacement by current distance. Both of these have the same magnitude. Direction will only be the value of +1 or -1. So the direction is can only be +1 or -1. This helps to determine if the spring is compressive or if it is expansive. So if you pull this spring closer than the current length, then it might if it's pulled closer than the resting length, then it has a tendency to expand. So spring force here I'm calculating is going to be K, which is the Hooke's constant, into current distance minus resting length. Resting length I've already defined a constant somewhere else, star direction, and direction determines if it's compressive or expansive. And here are the coordinates which I showed in Canva. How do we compute each of these coordinates? By just rearranging terms of that second order differential equation, and then we update the state. We set b1.x previous is going to be b1.x. Wait, this might look a bit confusing. b1.x previous is going to be equal to b1.x. b1.x is equal to b2.x is going to be equal to x2 new. This is updating the state at every instant. So 60 times a second, because it's a 60 fps program, we are going to be rerunning this particular block of code. So I do not think I have exceeded my limits inside Colab, but I'll show you how the video should look like of the two springs. So guys, I hope you're ready for the big reveal. So here you got two blue blocks. This one initially had a lot of velocity in the right direction, and they're slowly going out of our screen. I just like to admire it, so I'm going to show it once again. Alright. Can we use displacement in place of current distance? Direction in... Yeah, you can use displacement. I just made it so that it's intuitive to recognize that +1 means compressive and -1 means expansive. So yeah, I think that's it. I'll share this code later through my notebook. And let's go back to Canva. I think that's it. So guys, just mark your attendance here. Assignments I'll send them later. One assignment will be... Wait, good question. Even I forgot the first assignment. The second assignment will be based on the finite difference method that we did today. I'll ask you to combine both the springs. You remember the spring simulation, right? Combine the spring simulation along with block collision. Try to stick to as much of the logic that I taught today, and try to use a finite difference method. There are many other physics methods that you can use. Maybe that might be easier as well. But do try to use this because this is the most logical. Also try to... I'll be giving spring contact between the blocks, but their velocity are not restricted in one dimension. They can go in any direction, like it will be 2D. Okay, assignments are done. Please share the code and the slides. Everything will be shared. Please mark your attendance now. Guys, I'll end it on this. I ran out of time a long time ago. Sorry if you guys had to stay and extend your own commitments for me. Thank you guys for whoever stayed back. It's amazing that 60 people listen to me. That's more people that have listened to me in my entire life. Okay then guys, wait, I'll try to put on my video one last time. I'll keep this presenting. Just give me a second. OBS, my stream, properties, window, and Okay then, guys. I hope you had fun. And sorry for all the disconnections in the middle. I was pulling my hair out. I think that's visible kind of here. Okay then. Bye, guys. Have fun. Hope you enjoy the session. If you ever come to IITM, please do join iBot. I'm there as a coordinator for the upcoming year. I would love to meet you all. Amazing enthus shown today. I hope you keep this in throughout the first year of college. We'll have fun projects in iBot. Way more fun than this. Hoping to see you all. Have fun in summer school. Check out the other clubs projects as well. See you guys. Bye. Heads. Are we taking attendance? How long should I keep this running? See you guys. Bye.